Good afternoon, everyone. Welcome to the joint seminar today. We are very happy to have Mark Mezei from Stony Brook to tell us about his work on the volume of black hole interior at later times. So Mark, the floor is yours.
Thank you very much for the invitation and for all of you for coming. I see many familiar faces I'm very happy to talk to you, and I would like to encourage questions. I know the background of some of you, but not of all of you. So please let me know at any times if something is unclear, if you want more details or so on. So this talk is based on a paper from July with Luca Iliassiu and Gabor Sárosi. So as an introduction, let me just invite you to the problem. So in ADS-CFT, it is a fruitful endeavor to search for ubiquitous features in geometry, and then try to understand them from field theory, their quantum field theory counterparts. And so in gravity, black holes form from generic initial conditions in ADS spacetime. And this has been understood to encode the process of thermalization in the boundary quantum field theory. And once this connection was established, then we can start to ask more detailed geometric questions and more detailed questions about real-time dynamics of QFTs. And so one question that we will be asking is the following. So on the gravitational side, we know that the interior of black holes grow in time. So here's a sketch of a Penrose diagram of a collapsing black hole. So this is the asymptotic boundary, and this is an infalling matter. So okay, so there's an initial time slice. I prepared some matter distribution rather close to the boundary. And then I evolve this initial state. It collapses to form a black hole. This is the black hole horizon. Okay, and what do I mean by the interior growing? I mean that I anchor Cauchy slices at different boundary times, and then I maximize over the volume, and I get these blue curves on the Penrose diagram. These are maximal volume slices, and their volume grows. Their volume grows actually linearly in time, and the dominant contribution is coming from the behind the horizon region, actually in somewhat away from the collapsing matter. And so what we are interested in is what this growth encodes in the boundary field theory. And by answering this question, we hope to learn both about strongly coupled QFTs and perhaps also about quantum black holes. And sometimes people draw a speculative analogy between this growth of space-time behind the horizon and cosmology in expanding spacetimes. Okay, so the first candidate to capture this growth is entanglement entropy. Now let's compare the two. So the blue curve here is how the volume grows as a function of time. And at early times, entanglement entropy tracks this volume rather closely, but then it saturates at some finite time. So let's imagine that we put the field theory on a sphere. So we are working in global ADS. The sphere radius is capital L, and the maximal subregion size that we can choose is roughly of size L, linear size L. And this saturation of entropy happens at that time scale. So in summary, entanglement growth tracks this volume of maximal volume slices rather closely at early times, although there are some crucial differences, and I spent years of my career understanding the details. But for this talk, let's just stick to the story that it tracks it very very closely. But then it saturates too early. What do I mean by too early? I mean that we don't expect that something dramatic happens in gravity at that time scale. We think that the classical computation of this volume should be accurate even going forward in time to a lot longer time scales. And another quantity that we conventionally consider to probe quantum evolution is correlation functions. If we choose correlation functions at widely separated points, which is again the widest separation that we can do in space is of order L, they will saturate at the same time scale. This is the light crossing time, and even non-local correlation functions or non-local probes, Wilson loops, anything conventional will saturate at this time scale. Okay, so maybe this is the right time to talk about some time scales in real-time quantum dynamics. So just to remind you again, we are studying the out of equilibrium dynamics of finite energy density states in a QFT in finite volume. So the earliest time scale that we usually talk about is the time scale of the inverse temperature, inverse effective temperature of this finite energy excited state. And this is the time after which hydrodynamics starts to apply and the one-point functions reach their equilibrium value or hydrodynamic value. And then we already touched upon this time scale L, the light crossing time. This is when conventional but non-local objects saturate. Then in recent years, it proved to be fruitful to go to longer times. And famously, these with out-of-time ordered correlators, one can probe quantum information scrambling or operator scrambling. And the time scales probed by these probes is of order log S, where S is the entropy of the state, the entropy of the corresponding black hole. And in holographic systems, large N systems, this scales with log N. And this is the scrambling time. And then in even more recently, people started to talk about the spectral form factor. So spectral correlations in these chaotic, strongly coupled systems. And so for example, the dip in the spectral form factor, for those of you who know what it is well, this is a contentious issue, but let's just say that it probes timescales of order S or order N, depending on what dimension you are in and what holographic system you're studying. It could be N to some other power. Finally, the latest time that that we know how to think of is already familiar from the early days of quantum mechanics. E to the S is the Heisenberg time. The way we think about Heisenberg time is this is the time at which the initial out of equilibrium state has become a typical state. Now there are qualifiers. We have energy conservation. So it became typical with the constraints of energy conservation obeyed. Another way of saying it is that all phase differences by this time, so namely, let me just write one formula. So let's say that we have a phase EM, e to the I, EM, EN, T. So for any energy eigenvalue M and N, by the Heisenberg time, because the mean level spacing between, or like the average level spacing between energy eigenvalues is e to the minus S. At this time, e to the S, this phase is random for any choice of M and N. And so this is what we roughly, that's the intuition, that at this time, all phase information has completely became scrambled, and And so the system is as random as possible, and if or the state is as random as possible, and if the state is as random as possible, that any sensible probe should stop evolving in time. And finally, there's this even longer time scale that occasionally gets mentioned, the time scale of Poincare recurrences, when you learn that actually your state is not quite random. You recover the initial state, but I think it's fair to say that nobody has a good idea of how to address physics on these time scales. And so in this talk, the main, when I say that black hole interior at late times, I will be probing the Heisenberg time scale. Is there any questions so far? Okay, so entanglement entropy didn't quite capture what we wanted, and this motivated Susskind, and then Susskind and collaborators, and then many interesting works have been done since to think about something very unconventional in quantum field theory, complexity. Now, for the benefit of those of you who have never thought about this, I have a cartoon here. This cartoon is for a spin system. Here are my spins, many of them. They are represented by these legs, and the time is evolving upwards. And so we ask the following question. We start from a reference state, which is just a product state on these qubits. And we want to arrive at the state of our system at time t. Okay, so somebody hands us this state. It was obtained by some time evolution in our chaotic system. And then we ask, okay, how complex is this state? So we are given a state psi of t and the reference state, and we want to devise a quantum computation, a quantum circuit that produces this state with some epsilon error tolerance. We are given let's say two kind of quantum gates, a pink and a blue one. This is the gate set, and we don't count, so swap, like this like crossing of legs doesn't count as something expensive. So we set up this grid, and whenever we want to apply a quantum circuit, then we color the vertex. Okay, so we do this until we obtain this state psi of t. I mean, it's extremely complicated to do this, but we don't care. So we obtain this, and then this was one realization of the quantum circuit. Then we minimize over the number of gates applied. This is even harder to do in practice, but this is just a theoretical proposal. And so the minimum number of gates is one way to define the complexity of the state with error tolerance epsilon. Okay, so this was in a discrete system, something already hard to compute. And then you should imagine that you do something like this in quantum field theory. We don't care about, for this talk, we don't care about how you do it. This is just providing inspiration for us. Even though this is a daunting computational task, there is some expectation of how this complexity should evolve in time. And the expectation is that complexity grows linearly in time until the Heisenberg time, and then it saturates. So it behaves just as I talked about for general observables. After the Heisenberg time, nothing should evolve, and this thing also doesn't evolve much. Maybe there are some small fluctuations, but for e to the s times, it grows roughly linearly and then saturates at a value of order e to the s. So here's a summary of what we know so far. So in classical gravity, the volume grows linearly forever. Entanglement entropy tracks it at early times, but saturates too early. And complexity is proposed to track this volume growth and then saturate at the Heisenberg time. Maybe I didn't mention that the spectral form factor also saturates at this time, but it's not really probing the classical black hole geometry. So we'll be looking at some other probes, and also it has huge noise on it of order the signal, whereas complexity is expected to have only order 1 fluctuations. Okay, is there any questions so far? So I know that this wasn't a very precise discussion. This, for me, complexity is just an inspiration. What we are really going to do is to ask the question, is there some quantum gravity effect that stops the growth of the volume at the Heisenberg time, and whether we can say something about the relation to complexity. So this concludes the invitation. Is there any question? Okay, so I can tell you the outline now. I will review spectacular work that led to the correspondence between JT gravity and matrix integrals, the description of GQFI-Teitelbaum gravity as a matrix integral. And then we will compute the volume of the black hole interior in this toy model in the matrix integral description. Once we set up the problem, we will evaluate the volume, and if we have time, I'll discuss some issues related to ensembles, the variance of the quantity that we are looking at, and finally I'll summarize. Okay, so we want to understand this problem. It's a hard problem, so we are in search of the simplest possible model. And one step to first simplification is to get rid of the collapsing matter from the setup and to study the problem in pure gravity. So what we do is to replace the collapsing black hole with the eternal black hole. How do we get time evolution in the eternal black hole? We follow the idea of Hartmann-Maldacena, who set up time evolution in the eternal black hole by evolving the two asymptotic boundaries, both of them forward in time. So forward in time, we anchor maximal volume slices at both the left and right boundary, and you can see that these maximal volume slices look very similar to what we have in the collapsing black hole. So it seems that we can get rid of matter. We also know what the state of the dual QFT is. It's a thermophile double between the left and the right CFTs. Okay. Next simplification is that we want the simplest possible model of gravity, which still captures this phenomenon. And there are two ways to think about this GQFI-Teitelbaum gravity. One is that near extremal black holes generically have a near horizon ADS2 cross some compact manifold geometry, and dimensionally reducing on this compact space M, we get a two-dimensional model of gravity, and it's this GQFI-Teitelbaum gravity. We will So this is an effective field theory for near extremal black holes. And just like in any effective field theory, there are corrections to the leading order action. We throw away these corrections, and also like massive fields. We throw away these corrections, truncate the problem, and we'll just study the leading order effective field theory action as a theory on its own. And we study it using the Euclidean gravitational path integral. And it turns out that because of low dimensions and some other miracles, this effective field theory on its own is a UV complete theory. And so it can also be treated as a toy model for quantum gravity. And so this is the perspective we take. And I intentionally defer the discussion of ensembles and issues with higher dimensions to the discussion. We don't need to talk about these to complete the computation. So the action that we get from this is as follows in 2 dimensions. So there's a topological term that just gives the Euler characteristic of our manifold times minus S naught, where S naught is the entropy of the extremal black hole. And then comes the non-trivial part of the action. It consists of a dilaton multiplying the term R plus 2. Okay, now if we integrate out the dilaton, you see that it only features as a Lagrange multiplier. So it will impose as a functional delta function that at every point on this manifold, R is equal to -2. So we are studying hyperbolic Riemann surfaces. Okay, there are also some boundary terms that I won't write down. And so using this philosophy, Schenker-Stanford showed that if we try to do the Euclidean gravitational path integral, we can actually make progress. So as I said, we integrate out the dilaton, and then what we are left with is just a sum over Riemann surfaces, which are characterized by the genus. So this Euler character term turns into e to the S naught times 1 minus 2g. Okay, what are we calculating? We are calculating the partition function. And then there's a couple of integrals left. Riemann surfaces have moduli, and so it's clear that we have to integrate over the moduli space of genus G Riemann surfaces. And then there are also some boundary graviton degrees of freedom that I will represent as follows. W stands for wiggles, as you will see, and they are weighted by some action, which I just schematically write as a boundary action of these wiggles. What are these wiggles? So one way to think about the boundary gravitons or these wiggles is that our boundary condition is that we are studying the one-dimensional boundary theory on a Euclidean circle of length beta. That's the only invariant of this. And so of the boundary theory. So that corresponds to cutting out this cutout region from the hyperbolic disk. And the only thing that is fixed is the length. And so we have these wiggle degrees of freedom. It can wiggle in arbitrary ways, and we have to integrate over these. Okay. So this is at genus, for the disk, this is a genus 0. At higher genus, the construction is a bit more elaborate. So we have a higher genus Riemann surface. And the way we calculate the path integral is as follows. So we start from from the boundary of the asymptotic boundary. Then we have the wiggly boundary. And then we go inwards and find the first geodesic. And this I call the length of this geodesic B. I cut the manifold there. And then on the other side, I'm left with a bordered Riemann surface. So a Riemann surface with a geodesic boundary of length B. And this remaining integrals over moduli space and path integral factorize in this following nice way. We get the contribution from this so-called trumpet, which is characterized by the length here, beta, and the geodesic length here, B. So this is after integrating over the wiggles. And from the moduli space integral, we get the volume of the moduli space of genus G bordered Riemann surfaces. And finally, we have to glue these two guys back together. And one can show that the measure for that gluing is BdB. The factor of B is coming from twist degrees of freedom, because we can glue this thing with an arbitrary twist. Okay, so this is the quick summary of the work of Sachs, Schenker, Stanford. They showed how to compute the partition function to all genus in JT gravity, and this is their answer. And these things that are denoted by Z actually have very simple expressions. Just for illustration, I wrote it down here. These are obtained by doing these wiggle path integrals, and they turn out to be one loop exact, as shown by Stanford and Witten. Okay, but the story doesn't stop here, because we still have the task of computing these moduli space volumes and then summing over all genus. Remarkably, that some progress can be done even in that direction. So the help comes from mathematics. Moduli spaces of Riemann surfaces were studied extensively. In particular, Mirzakhani's Fields Medal work consists of deriving recursion relations for these moduli space volumes. And then Einard and Orantin reinterpreted these recursion relations as coming from matrix models, as loop equations from matrix models. And Sachs, Schenker, Stanford, after arriving at this formula, reinterpreted this whole thing as a matrix integral. So remarkably, things reorganize in the following way. The partition function is equal to the expectation value of some object that I will soon write down over a matrix ensemble of Hermitian matrices with some matrix potential e to the minus trace of some potential. And we are calculating the expectation value of trace e to the minus beta h. Okay, so if we think of h as the Hamiltonian of the boundary system, then it's rather natural that the partition function will be the expectation value of trace e to the minus beta h. There's one extra step. We have to take a double scaling limit of the matrix integral. For those of you who don't know what that is, it just means that we scale the sizes of these H matrices to infinity. At the same time, we lower the energy to go towards the edge of the spectrum so that the density of states stays finite. Okay. So where we are now, this simple gravity model has an equivalent formulation in terms of the matrix integral. And this is not my work. I'm just reviewing something that I will use in the following. Is there any question? Okay, so this is the completion of the genus expansion in gravity, actually, because these matrix integrals are well defined, non-perturbative. Okay, so a natural question is, can we set up the computation of the volume in the matrix integral? So in other words, we have this matrix ensemble. Is there some object whose expectation value in the matrix and ensemble computes the volume? Okay, for that, we first have to go from Lorentzian to Euclidean. That's easy. The eternal black hole is obtained from the Euclidean gravitational path integral. It's basically the Hartle-Hawking wave function. So we take this time slice, and then we do the Euclidean gravitational path integral, and that will give us this thermophile double state. We have the wiggly boundary in Lorentzian, and it will continue to be there in Euclidean. And we anchor 2 points here and then calculate the geodesic length between them. And so this is what we'll do in Euclidean as well. Okay, so let's just check if we lost the interesting physics on the way of simplifying the model. We did not. So if we do the classical computation of some subtracted length of a geodesic, we get this answer, which at times greater than beta, we are anyways interested in late times, so this is not a big restriction, grows linearly in time with a coefficient 2 pi over beta. Okay, great. So this is the classical computation. We can also do that in higher dimensions. So let's go further. Can we incorporate quantum effects? And Zhenbin-Yang, in a very nice paper, incorporated all perturbative quantum gravitational effects, not just one loop, but all loops. Okay, what did he do? He first determined the Hartle-Hawking wave function. So on this hyperbolic disk picture, we set up a wiggly boundary, but then anchor 2 points and cut out, and do this cutout with a geodesic boundary of length L and the wiggly boundary of length beta over 2. You can compute this path integral, and it gives us the Hartle-Hawking wave function in the basis where L is like just like in quantum mechanics, you can work in position or momentum basis. Here we are writing down the Hartle-Hawking wave function in this geodesic length basis. Okay. And then you do what you would do in quantum mechanics. So you have a wave function. So you have a bra and a cat, bra and cat, and then you compute the expectation value as follows. So you write down the probability, which is absolute value squared of the wave function. And then you write down the operator whose expectation value you're computing, which is this geodesic length L. And it turns out that the appropriate measure is e to the L dl. And furthermore, you have to normalize by the norm of the wave function, which turns out to be the partition function. And I'm now realizing that I forgot to tell you one thing, that how we get Lorentzian physics out of Euclidean physics. We analytically continue time. So the length of this wiggly boundary in the Hartle-Hawking wave function computation is just some real number beta over 2. And then we analytically continue this to beta over 2 plus IT. And that's how we get Lorentzian physics. Sorry about that. Jump in logic.
Can I just ask something? Hi, Mark. I was going to ask you about this, but I have more to. So aren't, like, I guess this Sutschenken Stanford story and all this quantum recursion relation, that's for Euclidean regime?
Yes.
And then you're saying that there's no subtleties for this quantum expectation value of the length to be continued to Lorentzian?
Yes, that's what I mean. Okay, so you have to be careful how you define length. If you try to incorporate some absolute value or something, then you would run in trouble because you need something analytic that you can analytically continue. So in the paper we've done an analytic choice. Here I will be more intuitive, so you won't see that subtlety. But yeah, if everything is a holomorphic, or if everything is an analytic function, then like any object that you're writing down here in here, if they have good analytic continuation or unique analytic continuation, then you're in good shape.
Okay, thanks.
Okay, thanks for the question. Okay, so I didn't write down the explicit formula, but it's rather simple for this wave function. You can do this integral, and what you get is a change in the slope of the linear growth, but the linear growth persists. So to all loops in quantum gravity, there's a factor e to the s naught, that's just conventions, and then temperature dependent coefficient, which at high temperatures where you become classical becomes 2 pi over beta, just as above. Okay, so it seems that perturbative quantum gravity effects are not enough to cause any substantial change in the behavior of the length. And our work it was to address non-perturbative effects. Since we know that this genus expansion is under control, actually there's a matrix model that provides a non-perturbative completion of this model. It's worthwhile to ask whether non-perturbative effects change the behavior of this observable. So in pictures, what we are doing, this is the computation at genus 0. And what we are doing instead, just like in the case of partition function, is to replace this object with some more complicated topology. So how do we do that? We replace the half disk with this half trumpet. So you can see this tentacle emanating here with a geodesic boundary. I mean, here I'm not drawing the very accurately these surfaces. They are at every point they have a hyperbolic metric on them. But topologically they look like this. So we prepare the bra and the cat, and then we can glue any topology that we want here. We can glue disconnected topologies, one here and one there, or we can glue a connected one. Okay, so at the end of the day, if I denote these objects by psi, then I get two factors of psi, the length that I'm trying to compute, and then I get volumes of moduli spaces. If I'm drawing the connected one, then this connected bordered Riemann surface has two boundaries of length B1, B2. And then I can also get contributions from any choice of disconnected ones. Okay, so this is the answer we are looking for, the expectation value of L. We have to evaluate this and sum over all genus. So in effect, what we did is to replace this object with this object. Okay. Now, how are we going to sum up the genus expansion, or how are we going to handle these guys? So let's compare to what we would do if we set out to compute the two boundary gravity path integral. So let's have one boundary of length beta over 2 plus it, beta over 2 minus it, This is actually the spectral form factor. Everything would look very similar, except maybe I should have had a figure, but maybe it's enough to illustrate. So the only thing we are doing is having two of these guys, two holographic boundaries, and then gluing in the same topologies that we have here. Okay, so if you do this computation, this was already done in the literature, then you get an expression like this. The only difference is that now we don't have this geodesic L. Instead, these trumpet wave functions are replaced by trumpet partition functions, and then there's no integral over L. But the same combination of volumes of moduli spaces appear there. And so it's not unreasonable to expect that this computation is related to this computation in some way. Okay, let's connect them more concretely. For that, we have to think about the density of states, which is familiar from statistical physics. So that we can write the partition function as an integral over the energy of the density of states with the Boltzmann factor. And this is one of the most basic objects in random matrix theory. The expectation value of the density of states in random matrix theory, which in Gaussian random matrix ensembles is the familiar Wigner semicircle law. Here in this JT matrix model is 2 pi e to the s naught, so it's big, sinh of square root of e, and there's an 8 pi squared in my conventions. This is the leading order answer, and there are exponentially small corrections to it, which can be computed recursively. So if we okay, so with this additional crutch, so we define the density of states. We see that this object will be related to the 2-point function of the density of states. And it turns out after some manipulations that this is also related to the spectral 2-point function. Okay, so after this massaging, I hope even if you lost me in this massaging, the final answer should be understandable. So the expectation value of the length or the volume of the black hole interior is determined by the spectral 2-point function. There's a very important factor of 1 over omega squared, where omega is the difference in energies. So E is the center of mass energy between these two density of states, and omega is the difference in energies, and there's a 1 over omega squared enhancement. There are other unimportant factors, such as a factor of 1 over the density of states, a Boltzmann factor. We are integrating over E and omega, so the two energies. And the time dependence comes from a 1 minus cosine omega t factor. This is just the result of the calculation. It's not something that you should have a good intuition for at this point. Okay, so if you evaluate this double integral, if you know what the spectral 2-point function is, and you evaluate this double integral, then you will determine the length. Okay, so this is our task. So what is the spectral 2-point function? I sketched here how it looks in any random matrix theory. So E is the center of mass of the eigenvalues, omega is their separation. In chaotic systems or in random matrices, eigenvalues repel. So at 0 separation, there are no eigenvalues, and correspondingly, the spectral 2-point function is 0. Then it goes up. It has a peak at the typical separation of eigenvalues, which is 1 over the density of states. This is the mean level spacing. Then there's a dip because the spectrum is very rigid. So there's usually one eigenvalue at roughly the same separation. Then there should be a gap. Then there's a second peak corresponding to 2 times the mean level density, and 3 times, and so on. And this decays as 1 over omega squared to the mean value squared. Okay, so this asymptotic value for large omega is the density of state squared. So you should think of this as having a large disconnected contribution. If you just took 1-point functions, then this is what you would get. Okay,
Mark,
this is how it looks. Yes.
So when you get the expectation value of this some kind of volume or complexity, like where can I see the genus?
Oh, the genus, very good question. So this density 2-point function, spectral 2-point function, has a genus expansion. You will see that it shows up there. In particular, this repulsion of energy eigenvalues is coming from the resummation of the genus expansion. Whereas, so to leading order in the genus expansion, you just get this disconnected answer. At subleading order, the only thing that you see is this envelope. And if you sum up the genus expansion, then you see the wiggles. And then you see that it goes down to 0 at omega equals to 0.
Okay, okay. But how come the genus expansion will make the curves fluctuating?
Well, it just, yeah, okay. I probably understand your question. So this row of E expectation value is huge. Rho, I wrote it down, but maybe I went over it too quickly, is of order E to the S naught. So these separations are non-perturbatively small in the genus expansion. They are E to the minus S naught. So this is how the genus expansion parameter shows up. And so the wiggles are coming from resumming things and getting these features from resummation.
Okay, okay.
But okay, so this sounds extremely complicated, but we already seamlessly transitioned to this matrix model description. And in the matrix model, things are, this repulsion of energy eigenvalues is not a subtle phenomenon. This is the basics of matrix models. But in the gravity language, this is extremely complicated physics.
I see, thanks.
Okay, so so you saw the picture. Now I will show you the formula. So for omega, okay, so if we want to go to late times, because omega is conjugate to t, that means that we want to go to small omega. And at small omega, we have this universal physics that I drew here, the repulsion of energy eigenvalues, and the spectral 2-point function in any random matrix theory in the GUE, in the unitary universality class, is well approximated by a disconnected contribution. So that's this mean value plus these wiggly and 1 over omega squared decaying contribution, whose explicit form is sine squared, the mean density of states, omega divided by omega squared. So this 1 over omega squared is coming from genus 1, and this one is coming from all resummation of all genus. Okay, so we have to plug this formula back into our master formula. So I will denote by blue the disconnected contribution. This is what Zhengbin Yang has already evaluated, so it's growing linearly forever. Let's see what this guy, the green guy, gives. Now, you can see that for omega of order 1, this thing is order 1, whereas this thing is order e to the 2s naught. So it's clear that it's tiny at early times, or small omega, large omega, or order 1 omega, sorry. But as we go to omega very small, so times of order e to the s naught, that is conjugate to omega e to the minus s naught, from this 1 over omega squared enhancement, this thing actually becomes comparable to this thing. And once you do the calculation, you get the following curve. So it's very small here, and at the Heisenberg time, it starts to grow linearly or decrease linearly. And magically, and this is some cancellation that was not seen, as to the best of my knowledge, in random matrix theory literature before, magically the slopes exactly cancel. And so adding up these two contributions give us the orange curve, which shockingly looks just like the sketch of complexity. This cancellation is independent of the specific details of the density of states rho of E. So it's not particular to JT gravity. It's there in any random matrix ensemble, and we actually show the family of dilaton gravity theories where this is actually happening. So this is the main conclusion. Non-perturbative quantum gravity effects entered our story and changed the behavior of this non-perturbatively and diffeomorphism invariantly defined volume of the black hole interior. And it shows the same behavior as expected from complexity. Okay. In the interest of time, let me just skim over how the variance looks. So in this JT gravity, for those of you who are experts, know how to compute the noise on observables. You use this ensemble interpretation, and what you get is that the noise is small. It's e to the minus 2s naught on this linearly growing piece, and then even on this plateau piece, it remains small, although it grows as square root of t. So as you go to very, very long times, like e to the 2s naught, there the noise will be comparable to the signal, but on the Heisenberg time scale, it's still small. It's not order 1, but order e to the s. So yeah, the variance is small, but not order 1. It's bigger, e to the s naught over 2. Okay, so it's a so this length or volume of the interior is a self-averaging quantity, and it can be reliably computed for one member of the ensemble from the ensemble average, and this is as opposed to the spectral form factor. And finally, a curious observation in our mind, even though we haven't really done much with it, is that so this formula, okay, we got this formula for a matrix ensemble, but we can easily write down a quantity which is well defined for one quantum system, and that would take the following form. So we do a double sum over energy eigenvalues skipping the coincident ones. There's a 1 over E1 minus E2 squared factor. That's the 1 over omega squared factor in this formula. Then we have a center of mass Boltzmann factor. And the 1 minus cosine energy difference times t, giving us the time dependence. And this spectral 2-point function is simply not here. When we convert this double sum to a double integral over energies, that's when it enters. So for one member of an ensemble, this would be your formula to compute. You can compute it, and we've done so in SYK. And then if you do an ensemble average, then you recover this formula. So we define a new object, the C of t, which we call spectral complexity, that is defined for any system. You can compute it for any chaotic system you like, and it will show similar behavior to what is expected from complexity. Linear growth until the Heisenberg time, and then saturation at the plateau with relatively small fluctuations. And this seems to be the dual of holographic complexity, whether you like it or not. So if you define holographic complexity to be the volume of maximal volume slices, you pay attention to issues of diffeomorphism symmetry. So you try to come up with a gauge invariant quantity, and then you allow gravity to do its job. It will be in these low dimensional models, it will definitely be equal to this. So it's a reasonable conjecture that even in higher dimensional holographic models, spectral complexity will be something that is best related to holographic complexity. Okay, in the interest of time, we've been, since writing the paper, we've been thinking about in what sense this spectral complexity has to do with computational complexity or circuit complexity or something like this. And we don't have anything definitive, but I think we have some ideas. Let me instead skip this and just summarize. So we've been studying the fruitful interplay between gravity and QFT in the chaotic dynamical regime. We started with the growing black hole interior that motivated that in the field theory to look at complexity growth. And so this has become a very interesting and lively place in the literature. But from field theory, we have the intuition that complexity should stop evolving or stop growing at time of order e to the s naught. So we were inspired by this to look for new non-perturbative effects in gravity. And in this toy model, we found those. And hopefully we learned something new about both black holes and quantum field theory. And with this, I would like to thank you very much for your attention.
Thanks, Mark, for the very nice talk. I think we can still take some questions.
Hi, Mark. Can I still ask something?
Of course.
Great. So thank you for this beautiful talk. I had a question about this length that you computed. So somehow, I guess I understand that in the classical limit, it is just a length that stretches between one and the other boundary.
Yes.
But could you, for example, just compute it on some RT surface or something like that? Like, you know, can you imagine this length as being, you know, some quantum length operator that could be, that people sometimes, or area operator that people talk about computing, say, quantum Ryuta-Kayanagi, or this is not? This is
well,
not,
I mean, first of all, this is different codimension than Ryuta-Kayanagi. So this is codimension 1. So this is
okay.
I mean, it's length in 2 dimension, but
So it should be volume operator, or
it's volume. Yes.
Okay.
This is the volume operator, and this is, I mean, there are no matter fields in my story, so it was just really the volume of stretching between one side and the other. And we, in words, what we did is we computed the Hartle-Hawking wave function in this basis. So that's why the computation was so simple, that we just took the probability distribution of this volume that's coming from a Hartle-Hawking wave function, and then just integrate compute the expectation value with this probability distribution. That's what we were doing. And what we were doing is computing the higher genus contributions to this expectation value.
Okay, great. So that clarifies this. And then my second question is actually related to this. So I guess you said it's kind of universal, but in your case, you talk about this really JT gravity and this such kind of Stanford story. And as you probably know, there's this kind of parallel take on it using Liouville, or some, you know, 2, p Liouville, and then taking some large p. So actually in Liouville, you know, people have some explicit area operator as basically some expectation value of e to the phi Liouville or something like that, which have you thought about, you know, doing something like that in the Liouville language?
We have not, but I don't know how much is actually known about this Hartle-Hawking. So how much is known about this guy? If this is known, then one could go ahead and do the computation there. We did something more modest, which is to include these different dilaton potentials through introductions of defects in the ball. And in all those class of theories, the same story holds. And the only difference is that in this formula, it's the density of state of those different dilaton gravity theories and the 2-point function, spectral 2-point function of those theories that enters, but the formula is the same. I think some people are working on, like Luca is working on including end of the world brains in this story. So it's rather universal. I mean, in higher dimensions, of course. So from the perspective of near extremal black holes, here we are, you know, we dimensionally reduced on the compact manifold, and there would be degrees of freedom which describe the fluctuations of those. So it's not, I'm not claiming that this is all there is in higher dimensions, but this is part of the story. This is part of the story where you take the manifolds to be, you take pure gravity, and you always take this manifold to just sit there but do everything gravitationally in the remaining 2 dimensions.
Okay, thanks a lot.
Hi, Mark. Can I have a question?
Hi.
Hey, good to see you, and thanks for this beautiful talk. So I have a question to the topic contact terms. So are these so these contact terms give you a divergence, right? Like the quantity calculated divergence. So does it go in line with your definition of spectral complexity that you have presented towards the end of your talk?
Yeah, so the contact term is coming from when E1 is equal to E2.
Okay. So you excluded that.
So we discarded that by hand, but let me just say that if you evaluate, so that doesn't give an interesting time dependence. So even if so one way is to just expand this cosine for E1 going to E2. you will get a quadratic term from here, and you will get so that will actually cancel this 1/omega squared divergence. So you don't really get the divergence if you subtract the length at time equal to 0. But then you could ask, okay, actually, where does this divergence come from in the gravity story? Yeah, so I mean, we just think about this as some kind of usual QFT divergence, that if you are if we subtract the time equal to 0 value of this length, then it's gone. So we don't worry about it too much, but maybe we should.
So if you think about the complexity of formation, right? So
yes, yeah,
that could, would it show up, or like would it cancel?
It would.
So then would be like the
I don't have a good. Yeah, I don't have a good. No. Well, if I subtract the complexity of formation, so the complexity of the thermofield double state at time equal to 0, then it cancels.
Yeah, but if you subtract twice the complexity of the vacuum, it also cancels, right? This is beta independent, probably, right?
Well, there's that's hard to answer, because in JT gravity you don't really have the vacuum, because you always have black holes. You don't.
But if you subtract the answer for a different beta, say, so like instead of subtracting L at t equals 0 and a given value of beta, you subtract the value at some beta prime.
No, then it wouldn't cancel. It's data dependent. It's data
dependent. Okay. So that's one question, and unless you want to say something more about it.
No.
Okay. Better not. So the other question is about the variance, right? So I mean, this is a bit surprising how the variance behaves, like given this usual lore about complexity. So is it possible that there is like a subtlety in defining the variance, like a variance?
Yes, there is. Okay, great. Well, I mean, okay. So there. First of all, this was a rather hard calculation, in the sense that whereas the noise on the spectral complexity is kind of trivial, you just use so you have to compute. Basically, it's related to some complicated integral transform of the spectral 4-point function. Okay. And in the case of spectral form factor, you just use weak contractions for this 4-point function, and that already gives you the variance, and you're done. So it's coming from white noise kind of thing, very Gaussian noise. Here, the noise is extremely non-Gaussian. The leading contribution to the variance is coming from the connected 4-point function. The technical reason for that is this 1/omega squared factor, which wants to clamp all the eigenvalues together. And when you put all 4 on top of each other, the spectral 4-point function doesn't factorize. Okay, so anyway, I'm just saying that it's not a distribution, and the noise distribution is not a Gaussian, so it's not really well characterized by the variance. Of course, you can calculate the variance, but it's not a Gaussian noise, so it might be misleading. It might be that this large variance is coming from some rare event, or like some rare fluctuation of complexity, and that's why it looks.
So that is like that is rare, but so huge that actually the size overcomes the rareness. Okay. But
this is just speculation, because we don't really understand it. I think not just the size. What also concerns us a little bit is that it's evolving in time. It doesn't stop evolving. It's at the Heisenberg time. So we are confused about this. That's all I can say. And yes, it's unconventional for complexity, but I think it's correct for spectral complexity. So spectral complexity, if you computed it in SYK, computed the variance, we haven't done a systematic analysis of this, but I think it would show this, just because eigenvalues, it's coming from a universal behavior of random matrix theory, where all 4 eigenvalues clamp together and they just give this. So I mean, I think the big question is, in what sense is this holographic complexity defined by the volume is really computational complexity? Because if there are some subtle differences, then of course the behavior of one at late times, the noise on one at late times, doesn't determine the noise on the other at late. So I think a big challenge is to understand how, I mean, before the talk, we chatted with some people here about how closely these different notions of complexity are related to each other.
Yeah, I mean, good question, right?
Yeah, but okay, I mean, I can just, as a teaser, I don't know if we'll get anywhere, but we managed to relate this spectral complexity to something that looks more like a complexity, or one step closer to complexity, and that would be the following. So we are studying time-evolved thermophile double states. Okay, so you could ask, you time evolve, you take the set of thermophile double states below some time t. Okay, and you could ask, okay, what dimension Hilbert space these span? Maybe that's closer to a notion of computational complexity. And okay, where we made progress is actually the following version. So you form the following density matrix A of t by taking the time-evolved thermophile doubles and then adding the density matrix of time-evolved thermophile doubles and adding them together. And then ask what is the rank of this this mixed density matrix. Okay, the rank is a little bit hard to compute, but we can compute the second Riemann entropy. And if we compute the second Riemann entropy, actually this spectral complexity shows up exactly in that computation. Okay, so this is one step in the direction. Of course, the rank of this density matrix is not really complexity, but I think it's a little bit closer to what one would call complexity.
I see. So the first piece is time dependent, and the other, I mean, the inverse of the rank, like the first piece is going to be time dependent, and the other one, the time dependent one, is what you call spectral complexity.
Yes, yes. Yeah.
And this is the one that so this is the one that has subtracted the length at t equals 0.
Yes.
Okay. No, this is cool.
Yeah, can I ask the last question?
Yeah. Thanks, Mark, by the way.
Yeah, thank you.
And so at the beginning, you are looking for some quantum effects or quantum quality contribution to the complexity. Yes. And I guess is this the non-perturbative effect that you claim?
Yes.
And will this non-perturbative effect be related to some instanton, or is not at all related?
Well, I mean, it was actually doubly non-perturbative in the end, right? I mean, an instanton would be just a higher genus surface. I think that's fair to call an instanton. But here, actually, it was coming from summing over all instantons. Mm-hmm. It was not enough to just calculate the instantons inside themselves. You had to sum them up.
Yeah, that's exactly the place that confuses me. Because Yes, so first of all, I thought when we do this genus expansion, we already consider like some quantum effect.
Yeah.
But now seems okay. Maybe this quantum gravity effect you call it just means the after summing up, then you get like you said
no, you get effects from each of them, but if you just compute the genus one, you actually would get the divergence, but you somehow sum over all of them, and in the end the divergence cancels and the thing plateaus. It's a very subtle effect. But that's the same story in Sachs, Schenker, Stanford in the spectral form factor. It only plateaus because you resum the genus expansion. The difference for them is that they get this growth. So we get this linear growth from classical physics. They get the ramp, what they call the ramp, from genus one physics. So already that's, for them, it's an instanton. For us, it's classical physics. But for both of us, okay, for them, this thing is coming from the doubly non-perturbative physics. For us, it's coming from the doubly non-perturbative physics canceling the classical physics. So it's different, but it's like you need to get the plateau in both stories. You have to sum up the instantons.
I see. I got it. Oh. Yeah, I guess probably there's no more question.
Okay.
So thank you again for this very nice talk.
Thank you.
It's really exciting.
Thank you.